All right, guys. Today, yes, otherwise known as today, we are going to be doing pretty much what we've been doing, only they're going to be word problems. Instead of saying this is the derivative, you're going to have a word problem that's a rate, and we know rates are just derivatives. And so while I'm just going around just checking the homework a little bit, I just want you to take some time and read through this. Actually read it. Come up with something. Okay. Okay. Did you figure it out? Let's talk about it. Tim, you ready? Let's get going. So if water is poured into a bucket at the rate of 5 cubic inches per minute and is leaking out at the rate of 1 cubic inch per minute, at what rate is the amount of water in the bucket changing? Are we guessing random numbers? Okay. So if the water is pouring in 5 cubic inches per minute and it's leaking out at 1 cubic inch per minute, at what rate is it changing? Say proud. 4 cubic inches per minute. Was that just a guess? Do we think? I want you to understand that because, yeah, to get the rate at which it's changing, you take the rate in and subtract the rate out. 4 cubic inches per minute, and it's positive 4, right? So, because it's the way we're getting that, I'll put that in parentheses. We're taking the 5, that's the rate in, and subtracting the rate out. So we wind up with a positive 4. So is the water in that bucket increasing or decreasing? Increasing. Okay? The rate at which the water is being poured in is greater than the rate at which it's leaving. Now we got to think. Now it's thinking time. If the bucket initially holds 10... Yeah. The answer? Oh, good. Okay. I hold that. I'm going to... So if the bucket initially holds 10 cubic inches of water, how much water will there be in the bucket after 2 minutes? Okay, Gene, what do you think? Anyone else think 18 cubic inches? I think that. Now, how did you get that? Hmm. Very nice. And you started out with 10. So another way of thinking, so the answer is definitely there'll be 18 cubic inches. So she took the amount started with, right, which was 10. Oh, that was like the volume at time 0, right? And she added the change in the amount of water. See where I'm going with this? You like it? She added the change. She took the rate of change, which was a nice constant, and multiplied by the time. So she got 18. But really, she could have said, well, what I'm really doing is I'm taking the volume at time 0, and I'm integrating the rate of change from time 0 to time 2. And the rate of change is rate in minus rate out, so that was 4. So I'm going to just pause that there, because I know you're probably thinking, I don't need to know it that way, because I can always do it the other way. Okay, so to get the volume at time 2, you could just take how much you started with. That's your volume times 0. And add the change in the volume, which is what yeah. So this, what you're doing, you don't need calculus to do this, right? I think you've all lived in the world, you know how to do it. With constant rates, you would never need calculus, but our rates are not going to be constant, so we will need calculus. But for the concepts, we're going to think about just constant rates of change. Alrighty, let's look at this one a little more. What I've done here is I've actually graphed the rate at which the water was being poured in. I like to call the rate at which a quantity enters E of t, like E for enter. So that's 5. And the rate out is 1 cubic inch per minute, so I graph that down here as a function of time. Graph these rates. Now suppose, okay, so the water's coming in at 5 cubic inches per minute and leaving at 1 cubic inch per minute. Suppose all I want is the quantity that enters, like I don't care how much is leaked out, I just want the total amount of water that enters the bucket from time 0 to time 2. Billion? Okay, what would you get? So if it's, okay, don't. Okay, so what would you get? How much water enters the bucket? Don't worry how much is leaving. Okay, think about the total amount of water that's actually entering this bucket. What do you think, Ellen? 10. Now, how'd you do that? Okay, you took the rate at which it enters and you multiplied by the time, right? Yeah, and another way we could have done that is we could have taken the antiderivative, right, of the rate at which it enters, 5, from time 0 to 2. We want the total amount that enters. We can integrate the rate at which it enters. That's my 5. Let's just see if that would actually work. If we got that definite integral from the graph, how do you get the definite integral of 5 from 0 to 2? Using the graph. Area. Underneath the graph. I knew that's what you were trying to say. So the total amount of water that enters the bucket is 10. Right? So it was right. So that's one way to get it. We could have also used the fundamental theorem of calculus to get it. We could have taken the antiderivative of 5 with respect to t, so 5t. And we could have plugged in the upper and the lower, and subtracted, right? And we get 10 that way. Just want you to make these connections between graphs, expressions. But yeah, when you want the total amount that enters, you just integrate the rate at which it enters. Now, what do you think the total amount of water, or the total quantity that leaves from time 0 to 2 is going to be? Let me erase this. That was good. So first of all, what do you think the answer is going to be? 2. Right? Then you probably took the rate at which it leaves, 1 cubic inch per minute, and multiplied by the time, and that's how you got your 2. Well, let's do it the old calculus way. If you want to get the total quantity that leaves, what would you integrate? From 0 to 2, 1, because that's the rate at which the water is leaving. Now, we could either get this from the graph, because we have a graph of 1 right here, and we could just take the area under the graph of 1, 0 to 2. We got all that, because it's whole area above times area below is 0, it's 2. Or, how else could we get that answer of 2? Fundamental theorem of calc. Take the antiderivative, t, 0 to 2, and we get 2, because 2 minus 0 is 2. So we know over the first 2 minutes, a total of 10 cubic inches of water enter this bucket, and a total of 2 cubic inches of water leave this bucket. Now suppose I want to know the total change in the amount of water from time 0 to 2. What's the change? Subtract, right? You could take the total amount that enters and subtract the total amount that leaves, and you would, and what would you get? You get 8, right? So there'd be a change of 8 cubic inches over the first 2 minutes. Now, I gotta turn this, I gotta turn this back into calculus. So we know what the answer is. What would we integrate to get the total change? Oh, that is good. Why time mice? Okay. So yeah, you would want to integrate the rate in minus the rate out. Because if you, so the rate in, that's the area under that graph of 5, minus the rate out. So you can break them up. You could do them separately, right? It's a difference. So, or you could just integrate 4. But you want to integrate rate in minus rate out. Because when you integrate rate in, you get the total amount that enters. When you integrate rate out, you get the total amount that leaves. So yeah, if you want the total change, you want to integrate rate in minus rate out, and that would give you the 18. So we know there's a change of 8 cubic inches of water over the first 2 minutes. Here's the big finale. What do you think the total amount of water in the bucket's going to be at T equals 2? We didn't start out with an empty bucket. Oh no, we didn't. How much water was it? What do you think, Jan? 18. Kind of answered that already, didn't we? Yeah, but yeah, we did. But I want you to see it now in a new way. If we want to know the volume of water at time 2, we can take the volume of water at time 0 and add the change. And to get the change in the amount of water, you got to integrate rate in minus rate out from 0 to 2. So yeah, we did say that was 10 plus 8 equals 18. And I kind of threw that ahead before we even got to this on the first page. So just seeing it again. Now, I told you that they're not always going to be constant rates. It's not always just going to be a rate of 5 cubic inches per minute in and 1 out. Sometimes they'll be changing these rates. So here's a case. On mine, the rate in is, that graph is green, and I've made the rate out red. And we have some quantity, okay, and quantity at time t. Q of t represents the quantity present at time t. Let's say we were given the quantity at time a. How much was present at time a? Along with the rate at which the quantity is leaving, as well as the rate at which the quantity enters, E of t. We're going to see if we can come up with some expressions to answer the following. Suppose we just want the total quantity that enters from time A to B. We don't care how much was there to begin with. We just want the total quantity that enters from time A to B. Before you tell me how to do it graphically, tell me like an expression that could be used. If you want to tell me graphically and we can relate, we can get it back. What do you think? Yeah, A to B. Yeah, that's exactly what I was looking for. If you want the total quantity that enters, integrate the rate at which the quantity enters, which we've called E of t. Is that what you were going to say, Gina? Yeah, really. That's very good. All right, so that doesn't take into account how much leaves. It's just the total amount that enters. Let's say you just want to know the total quantity that leaves from time A to time B. Somebody else, somebody else. Jessica. Yeah, it'd be the integral from A to B of L of t dt. Cameron. Perfect. If you want the total change in the quantity, what you'd want to integrate from A to B is E of t minus L of t. Because again, you could do them separately. You'd be finding the total quantity that enters and you'd be subtracting the total quantity that leaves. So the rate of change is always rate in minus rate out. You got that one? Now, let's say the total amount, we want to know what is the quantity at time B. All right, we want to know the total amount of this quantity. It could be water, it could be garbage or soda, whatever it is, this quantities. We want to know how much we have, the quantity. All right, Gina, I'll let you try this one. Almost. What was the very first thing you said? Equals. You want to, well, what's your starting value? What's the one that you're given? Look way up in the given stuff. Yeah. You'd want to take, if you want to know the quantity at time B, you'd want to take the quantity at time A, which has to be given to you, right? Or you'd be stuck. If all you had was the rate in and rate out, you'd be stuck. And then you'd want to add the total change in the quantity, which is what you get by integrating rate in minus rate out. Riley? Yeah. If they don't give you any point on the actual value, the actual function, you can't, all you could do is talk about the change. But, the amount of change, the amount that enters, the amount that leaves, the total amount of change, but you wouldn't be able to find out how much you have at a particular. Because, if I say, hey, my salary went up $1,000, what's my salary? I don't know. You have to be given a starting value, right? Okay, I guess that's good. All right, let's. That is nice, right? Okay, now, so whenever you're talking about the rate at which a quantity changes, dq/dt, the change of the quantity over change of time, if you're given the rate at which it enters and the rate at which it leaves separately, how do you get the rate at which the quantity changes? You know the rate in, you know the rate out, but what's the rate of change? The difference, right? It's rate in minus rate out. It has to be in that order. So let's say this was a graph of our rate in, which I've called E of t in green, and rate out. And I want to make a little sign chart to see how the quantity is changing. So let's look at the first interval from 0 to where they intersect. Look at the rate out, look at the rate in. Is that going to be, is rate in minus rate out positive or negative? Negative. You see that? Rate in minus rate out is negative value. What does that tell you about the quantity for these times, for this interval? Ellie? Yeah, it's losing more than it's gaining, so the quantity is decreasing. Whatever it is, it's decreasing when rate in minus rate out is negative. Your quantity is decreasing. Okay, now let's look to the right of this point of intersection. What can you tell me about dq/dt, which again is rate in minus rate out, for those times? Positive. So what's the quantity doing for those times? More is coming in than leaving, so it's increasing. So I can always make a sign chart. So Q of t, your quantity, is increasing when which rate is greater? When E of t, the rate in, is greater than the rate out, which would make what positive? If you move things to the other side. I want to compare it to 0, so subtract L of t from both sides. So a quantity is going to increase when rate in minus rate out is positive. So whenever the rate in is greater than the rate out, it's going to be increasing, which means that the rate in minus rate out is positive. When is a quantity decreasing? Filling in this first inequality here, which has to be greater. What was it? Yeah, well, L of t, the rate out, is greater than the rate in. Your quantity is going to be decreasing. So what would have to be negative? Let's get the order right. Yeah, so rate in minus rate out is going to be negative. L of t is negative. So when rate in minus rate out is negative, your quantity decreases. When rate in minus rate out is positive, your quantity increases. Fun. Okay. Oh, we have to go to the homework questions. I know there was a question on 12, and then we're going to do an actual AP problem. Like, I'm so excited about this because we have so much background that we can answer these. It's just... Now, I gave you the answers to this homework. It's somewhere there in your notes. On page 3 or something. So you want to check that over. And, no, I got to reach all the way over here. I can do it. Audrey, you wanted to see 15, right? Yeah, let's do that. I had it. I'll keep it this size. Okay, question. Wait, how do I move this thing over? All right, I'm putting it back. Okay, so number 15. Actually, it was 13 through 15. It was based on this information here. Okay, so you were given that for the last 3 problems. You're asked to find the definite integral from 5 to -1, 3f of x minus 5. Well, you know, if we're going to use this whole, well, we're given actually the definite integral from -1 to 5. So I'm going to switch them. Okay. If you switch the limits of integration, you change the sign of the whole thing, right? We're okay with that? So I would just change it to, I'll just put the negative on the outside. Negative the definite integral from -1 to 5 of 3f of x minus 5 dx. Okay. Now, the great thing about sums, when you integrate a sum or a difference, you're allowed to break them up. That's one of the properties. So I could break this up, and I am also going to distribute the negative. See if you can get this. It would be -3 times the definite. Let me go over. I'll just move this one out of the way. Can I? Okay. What's calling me? Oh, look at that. That's kind of neat. Cool. Yes. All right. I'm going to just. So this would be -3 times the definite integral from -1 to 5 of f of x dx. Plus or minus. Because I'm distributing it. So plus, because I have the minus out here, and this is for the whole integral, plus the definite integral from -1 to 5 of 5 dx. When you integrate a sum or difference, you can just integrate each term separately. And with the first term, what I did was I also pulled out the 3. And did a couple things at once. Why would I what? Break it up? Oh, because this negative here, maybe I should have distributed that first. So let's make this positive. So this is negative, and that's positive. Okay. Did I leave the negative out or something for the end? Okay. Yeah, I guess the order I was doing things. But either way, you could get to this point when you break it up. Yep. Now this, they gave us right here, that's 6. So I have -3 times 6, and that one I have to do on my own. You actually have to take the antiderivative of the 5, plug in the 5, the -1, and subtract. So you get, I'm just going to go down here, right here. This is the coolest. Huh. Right. So we get -3, we just looked this one up, it said 6 times 6, plus, what's the antiderivative of 5 with respect to x? 5x. And I have to plug in the 5 and the -1 and subtract. So you have -18, and it's going to be plus 25 minus -5. So that'll be plus 5. Alright, so we had to actually take the antiderivative of that constant term. That's a fun little AP thing. I like that. You have to know that you can break up a sum or a difference, integrate each part separately. and they give you one of the pieces, and you got to figure out the other piece by taking the antiderivative, plugging in the upper and lower, and subtracting. So this came out to be negative 18 plus 30, which is 12. That was a toughie, huh? Yep. Never multiplication or division, but addition and subtraction for sure. Well, if you're multiplying by a constant, then you can just pull out the constant. But if you were multiplying with two variables, you could not just break it up. The integral this times the integral of that. Okay? But with a constant, yes, you can pull out the constant. You'd have to use U substitution or multiply it out first. Yep. You know what, kids? I hate to cut going over homework short, but I'm so excited to get through a full AP problem. Do you mind? If you look through the answers and you don't get it, like tonight when you're looking at, ask me first thing tomorrow. But I'm hoping we can see a full AP problem before I set you loose. Yep, 2005. We're doing this one together. All right, so and I always like to, and I'll tell you ahead of time, this tends to be one of the two questions on the AP exam, two free response questions that you're allowed to use a calculator on. I'm not saying always, but usually. And I usually like to put whatever the rate in, I like to put in Y1 and the rate out in Y2. So let's take a look at this problem. It says, the tide removes sand from Sandy Point Beach at the rate modeled by the function R. So R is for removed, I guess. So that's the rate the sand's being removed. That's your rate out. Okay, so you know what? I'm going to write L of T next to it. So remember that. That's my rate out. That's just for my own personal. A pumping station. Does everyone have their own pumping station? Pumping station adds sand to the beach at a rate modeled by the function S, given by S of T. So that's your rate in. Both R of T and S of T have units of cubic yards per hour. So they're both measured in cubic yards per hour. And P is measured in hours for time 0 through 6. At time 0, the beach contains 2,500 cubic yards of sand. That's your initial value. You need that, right, to work off of? Okay. First part. Maybe we should just enter, well, we'll do that after. I'd like to enter rate in Y1, rate out in Y2. You guys have calculators? Anyone need one? You can take one off my desk. Let's just do that first, and then we'll answer the questions, because it'll be easier. So yeah, put your rate in. That was your S of T and Y1. Put S. I know that's not the order they gave them to you, but if you're consistent the way you do these problems, sorry. Yeah, because that's the rate in, and if you're, you want to put your rate in Y1, your rate out in Y2, and the rate of change would be rate in minus rate out. That's another thing I love doing. I make Y3 rate in minus rate out, Y1 minus Y2 every time for these. Every time, so I got it. I don't have to worry about typing anything later. S of T goes in Y1. That's your rate in. R of T in Y2, rate out. Oh, and make sure you're in radian mode, physics kids. Always radian mode. A window? If you were going to set your window to see any of these, you would want to set your x's from 0 to 6. Your x min, 0, x max, 6. Yeah, you always want to match it to the problem. The y's, it depends if you have a graph or not. You can figure that out later. We don't need the graph yet. We just need those in there. If you're looking at my graph, I've only graphed rate in minus rate out. So yours, if you've graphed all three of them, see, I deselected those two, so I wouldn't see them. I don't want to see them. I just, what matters to me is rate in minus rate out. Vars, you know where vars is? And you go over to y vars, enter function, enter y1, then do it again for minus y2. If you do this every time, you know, I think it'll help you. Well, you probably have three graphs on there? Yeah. If you don't want to see a graph, you go to the equal sign and hit enter so it's not highlighted anymore, and then you won't see that graph. If you don't want to see so many graphs, you just want to see one of them. Like, I only graphed y3, rate in minus rate out. What can you tell me about this function, just looking at my tiny little graph here, rate in minus rate out? For this whole time in the beginning up to here, what's going on with the amount of sand? It's decreasing because rate in minus rate out is negative all the way to this time. And then it starts increasing. All right, but let's answer the question. I'm getting ahead of myself. It's just too exciting. Let's say this one. Well, that was just the y3, which was rate in minus rate out, y1 minus y2. I only highlighted that one. You don't need that yet. That was just... Okay, now, let's say it says, how much sand will the tide remove from the beach during the 6-hour period? Let's write an expression down. If we want to get the total amount that the tide removes over the first 6 hours, what expression do I need to write? Yeah. Don't even say what it is. Just tell me the other side. Like, well, you were going to say all this, and you could, but that's a time waster. Just R of T. dt. Now, that's what they're looking for the amount of work. That you know that you integrate rate out. So your R of T to get the total amount. But now to get the answer, what are we going to do? Where was my rate out? I put in my y2, right? So we're going to integrate y2, and I'm actually going to type that on my calculator. I'm going to go to my calculator. What's going on my home screen here? That's crazy. Wait, where's my calculator? What's going on? I only have a couple buttons. All right. So we something. So I'll just tell you what I was going to do. So I was going to go to the calculator, and I was going to do FNINT, and actually just put down y2. That's my rate out. You know, with the vars. Comma x, comma 0, comma 6. Yeah, it was, and tell me the three places, so it was 31.816, and that, now, as far as the units go, indicate units means if you don't, we're taking off a point. Yep, that's what they mean. To get the units, you multiply the units of the rate, which was cubic yards per minute, by the time units, which was in minutes. If you multiply cubic yards per minute by minute, what are your units? Cubic yards. So the total amount of sand that was removed was 31, yeah. Oops, sorry. This should have been hours and that should have been hours. It'll still cancel, that's good. But yes, thank you. When you multiply fractions, you just, there's RT is measured in cubic yards per hour, and time is measured in hours. The units of the differential hours. Okay, part B. Write an expression for y of t, the total number of cubic yards at time t. So we have to come up with the number of yards at time t. It's just going to be an expression. What we start with, yeah. Y0, which we know is how much? So that's 2,500. I'm going to jot that down. Plus the change, the integral from 0 to t, nice, e of t minus L of t. Rate in, oh, I got to use their letters though. Rate in was S of t, minus rate out was R of t, dt. So I would write the 2,500 here, because they never said that was y of 0. We just had to know that. So the full answer would be 2,500 plus the integral from 0 to t of S of t minus R of t. And that would be our full answer for that. No, don't even, if they've given you what to call them, just use that name. Find the rate at which the amount of sand on the beach is changing at time t equals 4. Right? If you integrate a rate, you're not going to have a rate anymore. Do you want to integrate a rate? No, we want a rate, right? We want the rate at which the amount of sand is changing. They've given us rate in, they've given us rate out. Say it again. S of 4, it's the rate in minus the rate out at 4. Yep. Now, if I have a calculator and I put rate in Y1 on my home screen, I'm just going to do, the bars Y1 parentheses 4 minus rate out. I put in Y2 parentheses. It's just like function notation. It works. Can't show you. My calculator's not working. I know this comes out to be negative something, but I don't remember what it was. Negative 1.9087, so 09 we'll say. And then, so that would be in the same units as both of these. So that would be cubic yards per hour. What does that tell you about the amount of sand on the beach at time 4? It's decreasing because we got a negative. This would have been the max. We would have had to check the endpoints. We would have found y of t at 0 and 6. And when rate in minus rate out was going from negative to positive because we wanted the absolute min. Do your best to get pieces of these questions, guys. This is a good time. Yep. You found your homework now? This is incredible. Oh, yeah. I'll take it. Yeah. I do that every day, so if you ever miss a lesson, I just want to make sure I turn this off. I think it might be recording still. Okay.